Hello and welcome to today's A-level chemistry lesson covering atomic structure and the periodic table, brought to you by Dr-Tutor. This is one of the more introductory topics in the chemistry A-level syllabus, but it's quite a vital topic to understand as it gives you a basis for all the knowledge you require moving forward for all aspects of the chemistry syllabus. This video is structured more broadly, but I personally did do the Edexcel A-level, and thus some aspects may not be applicable to other specifications. These definitions are going to be vital to everything in this topic moving forward, so it's important that you memorize these. Feel free to pause the video here and just take a look through them and read them. So the structure of an atom is obviously very important. Now, as many of you know, there's electrons, neutrons and protons that form the structure of an atom. Neutrons and protons clump together to form a nucleus in the center of an atom. Electrons orbit this nucleus. The nucleus of an atom of a particular element contains a fixed number of positively charged protons, and that fixed number is called the atomic number. The nucleus also will contain neutrons, but the number of neutrons can vary, and when there's variation in the number of neutrons, this forms isotopes. The mass number of an isotope is the total number of protons and neutrons in the nucleus of an atom, and therefore that can vary from isotope to isotope. The number of electrons in a neutral atom is always going to be equal to the number of protons, because electrons have a 1- charge and protons have a 1 positive charge. Therefore they can cancel each other out. Electrons will orbit the nucleus as we see here, but this orbiting is slightly different from what we would have learned at GCSE or before that, as you'll see moving on. So understanding the relative mass of protons, neutrons and electrons is quite important. So protons have a +1 charge and electrons a -1 charge. That was mentioned before. The relative mass of an electron is pretty much negligible. In most specifications, writing negligible will get you the mark, and protons and neutrons have equal mass. Understanding exactly how mass spectrometry works is quite important. So initially, air will be removed from the mass spectrometer in order to create a vacuum, because you don't want air to interfere with the part the positive ion will take. A sample element or compound, which must be in gaseous form, is then injected into the mass spectrometer, and this sample is bombarded with a beam of high-energy electrons from an electron gun. The energy from the bombardment of electrons leads to atoms or molecules forming positive ions. These positive ions formed then fragment into multiple particles, forming a positive particle and a neutral particle. The positive ions formed are then accelerated using the accelerator plate. This uses high electrical potential. The ions then pass through small slits and emerge as a parallel beam of ions. As all the ions have the same energy, they have the same mass, and they travel at the same speed. The ions will now be deflected by a powerful magnetic field. Ions of greater mass but equal charge are deflected less than ions with lower mass, which are deflected more. The angle at which the ions are deflected is based on the strength of the magnet and the mass-to-charge ratio of the ions. You can easily be asked questions pertaining to the degree of deflection an ion may experience relative to another one, so it's important you understand that greater mass but equal charge will be deflected less, while lower mass with equal charge will be deflected more. The ions of lowest mass will be detected first. The magnetic field will gradually be increased, and the ions of higher mass are then detected. The detector is linked to a computer which calculates the mass-to-charge ratio of each positive ion and its relative abundance compared to the most abundant particle. This is then converted into a percentage for each positive ion. This is then used to calculate isotopic mass as an average and is displayed on a mass spectrum graph, which you've probably seen. So when you look at a mass spectrograph, they will often have multiple lines. This is because many elements do have isotopes, and so there'll be a line for every possible combination. Chloride, for example, should have 3 lines because there's a Cl35 isotope and a Cl37 isotope. So therefore the combinations are 2 Cl35 ions with a mass-to-charge ratio of 70, equally Cl35 and a Cl37 isotope with a mass-to-charge ratio of 72, and a Cl37 and a Cl37 isotope with a mass-to-charge ratio of 74. There would also most likely be additional peaks at 35 and 37 for individual isotopes not in a molecular form. There are many types of mass spectrometers, and that can be useful to know based on your specification. These include time of flight spectrometers, where they're all loaded with equal kinetic energy and the heavier particles move slower, and electrospray ionization mass spectrometers, whereby samples undergo soft ionization methods, so there's no fragmentation, and so it's used to identify complex molecules. If that stuff doesn't feel familiar to you, don't worry about it. It's probably not in your specification, but just check to make sure. Mass spectrometers can have many different uses. So one is detection of drugs and their metabolites in urine and blood samples. Most drugs, such as certain steroids, have a unique molar mass. Urine samples, once taken from an athlete, is placed in a low-energy mass spectrometer and ionized using this method. It's then analyzed, and if the mass-charge ratio of the peak is equivalent to that of the molecular ion of steroids or a specific drug, then the individual must have taken the drug or steroid. In the pharmaceutical industry, the identity of a new compound can be determined using mass-charge ratio values. After your pure sample is obtained, a solution of substances can be sprayed through a needle of high electric potential and analyzed to gain its mass-charge ratio. Another use is carbon-14 dating. The relative amounts of isotopes of carbon-12 and carbon-13 in a sample can be found using mass spectrometry. As carbon-14 is radioactive, its activity halves every 5,730 years and changes to nitrogen-14. This means it can then be used in conjunction with other methods to date rocks, etc., which is especially useful for dating fossils. When we discuss atomic structure, we need to think of it in terms of orbitals and subshells, as opposed to what we may have traditionally thought of as the drawing on the left. While this is okay for example, dot and cross diagrams, it's fundamentally technically wrong. Orbitals contain subshells. Each subshell can hold up to 2 electrons. The reason for this is that electrons both have negative charges and thus naturally repel, and while orbiting, each electron will have opposing spins as they essentially spin opposite to each other in order to keep orbiting the nucleus. Now, not all specifications will require that knowledge, but again, just check with your specification. S orbitals have 1 subshell and therefore hold 2 electrons. P orbitals have 3 subshells and therefore can hold 6 electrons. D orbitals have up to 5 subshells and therefore can hold up to 10 electrons, and F orbitals have up to 7 subshells and therefore can hold up to 14 electrons. Electron configuration is essentially what we use to describe the orbitals of an atom in its ground state or once it's been ionized to a cation or anion. It's really useful for us to be able to understand how many electrons are in each orbital and the structure of each orbital, in terms of enabling us to understand why given ions or atoms have different reactions, reactivity, ionization energies, etc. Now, an example of an electron configuration is shown on screen: 1s2, 2s2, 2p6, 3s1. Now, I believe that is the electron configuration of sodium by memory, but what this is important for is explaining what each aspect means. So the number in the electron configuration, the first number, the 1, 2, that refers to the energy level we're referring to. Then the S or P or D or F refers to an orbital within that energy level, and then the number at the end after the letter refers to the number of electrons in that orbital. So from the electron configuration shown, we can say that in the first energy level of sodium, the s orbital has 2 electrons, meaning it is a full orbital. Now, the first energy level only has s orbitals. The second energy level only has s and p orbitals. So now from there we can say the s orbital in sodium has 2 electrons while the p orbital has 6. Therefore both of those are also full. And then 3s1 refers to the third energy level. The s orbital only has 1 electron, meaning it's only half full. Now, the third energy level also has a d orbital, but crucially, this d orbital is at a higher energy level than subsequent s orbitals. Now, what that means is that when we're writing out the electron configuration, we have to be mindful that after a 3p is written, we would typically then progress to a 4s, and providing the 4s is full, we would then go to a 3D again. So because the 4s is at a lower energy level, when we're writing electron configurations, we think of them in terms of ascending energy levels, and therefore the 4s would come prior to the 3D, and that's true for all subsequent s orbitals and d orbitals. The diagram on the right shows that quite clearly as well. Now, this can be somewhat confusing when you're starting out trying to write out electron configurations, but a good way to kind of help yourself is either use one of the two diagrams on screen. I personally use the periodic table example, so you would find where the element you're trying to find the electron configuration of is on the periodic table, and then you'd simply follow it along. So, for example, if we were trying to find the electron configuration of titanium, we could follow along as with the diagram in the bottom left, and therefore we could see it would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2. And now this periodic table example helped me personally to make sure I always remembered that 3d orbitals will come after 4s, and again that's applicable for all subsequent d orbitals. The best way to make sure you fully understand electron configuration is just go and try and practice and write out as many as you can and check them against Google, or print out some online worksheets. There's also some examples on my website, Dr-Tutor.co.uk, if you want to check those out. Now, if you're writing electron configurations for elements further down in the periodic table, it can be quite difficult to list out such a long, kind of extensive list and such a detailed electron configuration. Thus, what we can sometimes do is use the final group, so group 8, we then write that in square brackets. The square bracket is crucial, and then only list the electron configuration post that point. So for example, if we were doing the titanium example, we could put argon in square brackets, which would be square brackets AR, and then after that only put 4s2, 3d2. The reason for that is that it means we don't have to list out all of the period prior to it, which makes it kind of just simpler and easy to write. Now, in this diagram, which you may be presented with, it's a different way of displaying electron configuration. So each box essentially relates to an orbital, and now remember, an orbital can only hold 2 electrons maximum. That's why each arrow or half arrow represents an electron within that orbital. Now each set of orbitals or boxes represents a subshell, and as you will see, the arrows are kind of done in opposite directions. The reason for that is to represent the opposite spins electrons have, and therefore explain they're not spinning in the same direction, but that may not be needed for your specification. So now when we look at this, it's an important diagram to understand exactly how orbitals will fill out. So even though an orbital can hold 2 electrons, an orbital will initially only have 1 electron, and then the second will be added, providing all other orbitals of that subshell are full. So when we look at the 3p subshell, we see that each of the 2 orbitals, that out of the 3 orbitals of a p subshell, have 1 electron. Now the reason for this is that's all the electrons there are in silicon. But now if we were to imagine that there were 4 more electrons, then the 3p subshell would be full, and it would look like the 2p subshell. That's just an important concept for understanding the exact way in which an orbital will fill out, because it is something you can be asked on, and is also important to understand in understanding the trends in ionization energies. Moving on to ionization energies. This is quite an important definition, so I would recommend learning it pretty much word for word, but the exact wording may differ based on your specification. But essentially, it's the energy needed to remove an electron from each atom in 1 mole of gaseous atoms in order to produce 1 mole of gaseous ions. Now, the term gaseous is very important, and therefore it can also be written as an equation, but you have to make sure you remember the state symbols. There is an ionization energy that correlates for each electron in that an atom has. So for example, for sodium, which has 11 electrons, there will be 11 ionization energies. So when we are asked to define second ionization energy or any subsequent ionization energy, we just have to be mindful that we're not saying to remove an electron from each atom, because of course subsequent ionization energies are removing electrons from ions. So we just have to substitute that into the equation, and instead of produce 1 mole of gaseous ions, we would specify the charge on those ions. Ionization energies are always going to be endothermic because energy is taken in the reaction, and therefore the energy sign will be positive. Successive ionization energies are when we're looking at a group of ionization energies, so first, second, and third, say. They become very important in understanding trends and evidencing the orbital structure of atoms and ions. Successive ionization energies will typically increase, as once you remove one electron, the second electron becomes more difficult to remove. Now, if we think of this in terms of charges, we have a positive nucleus. Now, the nuclear charge is going to remain the same because we're not removing protons. But once we remove an electron, the charge balance between positive and negative shifts, and as we're removing a negative charge, the ion is going to become more positive. Therefore, the positive nucleuses hold an attraction, the forces of attraction between the electrons and the nucleus are felt more strongly by the electrons, and so they require more energy to be removed. As such, the ionization energies increase. Additionally, and arguably more importantly, so electrons naturally repel each other. When they're repelling each other, they require less energy to be removed because, of course, they're repelling each other. But as the number of electrons decrease with successive ionization energies, the repulsive forces also decrease, and therefore the attraction felt is greater, and so more energy is required. So when discussing trends in ionization energies, they are determined by 3 key atomic properties, and these should always be referenced in any answer you give trying to explain trends in ionization energies. So the first is the size of the positive nuclear charge. As the positive nuclear charge increases, the attraction of the outermost electron increases, and this therefore increases the ionization energy. Nuclear radius is the second important atomic property, and this is the distance of the outermost electron from the nucleus. As the nuclear radius increases, the ionization energy decreases, and vice versa. And the third is the shielding effect. Electrons in inner shells exert a repelling force on electrons in outer shells. This is kind of what I mentioned. And so the effect of attraction is reduced. The attraction of the nucleus is also shielded by these electrons, reducing the attractive force, and therefore a greater shielding effect tallies to a lower ionization energy. You may be asked to describe the trend in successive ionization energies of a given atom. So, using sodium as an example, we expect the large jump between the first and second ionization energies, as well as the large jump between the 9th and 10th ionization energies, as we see in the graph. This is because sodium atoms have a single electron in their outer shell, which is furthest from the nucleus. The outermost electron is very easy to remove, as it's shielded from the charge of the nucleus and is the furthest away, so feels the charge minimally. There's then a period of 8 electrons in the same basic energy shell, which are closer than the outermost and not as shielded, so are harder to remove than the outermost electron. The reason for a gradual increase in ionization energy, despite the electrons being in the same shell, is that, as we mentioned, as electrons are removed, the overall charge of the ion becomes more and more positive. This means that the force felt by each electron is greater, and so the energy required to overcome this stronger attraction increases. Hence, the ionization energy gradually increases. Equally, the degree of electron repulsion decreases. Finally, there are 2 electrons in the innermost shell. These are the 1s electrons, although you shouldn't describe it like that in a written answer or an exam. This means there's another huge increase in the ionization energy. These 2 ionization energies are generally the highest, as they are extremely close to the nucleus, and the nuclear radius is thus really small. There's also no shielding effect anymore, and the nuclear charge is extremely positive, meaning the charge felt by the 2 electrons is extremely high. Now, that's a general way you can go about explaining successive ionization energies. If you're writing it for the purpose of an exam, make sure you include more key terms. Most of these videos are going to be directed towards making it as simple and easy to understand as possible, but don't necessarily quote what I'm saying in an exam situation. Understanding the trend in ionization energy, or first ionization energy, across a period is very important, and it's a concept that can very well be tested. Now, when explaining the trend, what we have to bear in mind is our three atomic properties. There is a general increase in first ionization energy across a period. Now, in order to go about explaining this, we have to consider nuclear charge. Nuclear charge increases across a period because the number of protons is going to increase. At the same time, it's important to remember that the electrons are all in the same shell because the number of shells is going to be equal across a period, and therefore they will have a very similar shielding effect. So we can then use a key term of effective nuclear charge to explain that the effective nuclear charge is going to increase, therefore the ionization energy generally increases. When we say effective nuclear charge, we're referring to the actual amount of positive attraction that an individual electron and electrons are feeling, and therefore this takes into account the ratio of positive to negative charge in a given ion or atom. Now we have to go about explaining the anomaly. So we can see that there's a decrease from magnesium to aluminium, and this we wouldn't necessarily expect, but we can explain by using the electron configurations. So when we write down the electron configurations of magnesium and aluminium, we see that the first ionization energy requires an electron to be removed from the 3s subshell of magnesium as opposed to the 3p subshell of aluminium. As we're removing an electron in aluminium from a 3p subshell, this is further away from the nucleus, and therefore there's a weaker nuclear attraction. This weaker nuclear attraction means less energy is required to overcome the attractive force, therefore aluminium has a slightly lower first ionization energy. The second anomaly we need to explain is the drop in ionization energy between phosphorus and sulfur. Now, when we write out the electron configuration for phosphorus, we'll see that it ends in 3p3, while sulfur ends in 3p4. Now this means that in both circumstances, the first ionization energy requires an electron to be removed from a 3p subshell. Crucially, however, because phosphorus ends in 3p3, we know that there's 3 electrons in that 3p subshell. This means that each orbital in the p subshell only has 1 electron, whereas in sulfur, because it ends in 3p4, we know there's 4 electrons in that p subshell. Therefore, one of the orbitals has to have 2 electrons in it. This means that those 2 electrons within that orbital repel. Due to this repulsive force, less energy is required to remove the outer shell electron, and therefore sulfur has a fractionally lower ionization energy. Now, if you're slightly confused by this, you can try writing out the electron configuration for yourself. Equally, I would then recommend you try putting them into a box diagram as shown on screen, and you will see how there have to be 2 electrons in one of the orbitals. Another important trend that you know is that first ionization energies decrease down the group. The reason for this is that the number of electron shells increase, therefore the atomic radius also increases, and as such the shielding will increase too. Therefore the attraction between the electrons and the positive nucleus and the nuclear charge decreases, and so less energy is required to remove the outer shell electrons. I would recommend trying to write a detailed exam-like answer for either explaining the trend in ionization energy down a group or across a period. Feel free to leave it in the comments and I can give it a check over if you want to. Based on your specification, you might need to know more about periodicity than just the trends in first ionization energies. So as a result, I've put in a small slide to cover some of the basic temperature trends, but this may not be relevant to your specification and it's going to be covered in far more detail in the next episode, which covers bonding and structure. What we essentially need to be able to understand in order to explain the graph at the bottom of the screen is that sodium, magnesium and aluminium are metals, and as such they have metallic bonding. Metallic bonding is extremely strong and therefore their melting point is relatively high and requires a lot of energy in order for the bonds to be broken and for the metals to melt. Silicon follows a giant covalent method of bonding which has very high electrostatic forces of attraction, which requires a lot of energy in order to be able to be overcome, and therefore has a very high melting point. However, phosphorus, sulfur, chlorine, and argon follow simple molecular bonding structures. Now, the intermolecular forces of attraction are very weak in simple molecular bonds, and therefore the amount of energy needed to overcome these bonds is quite low, and as a result, they have very low melting points. That broadly explains the graph at the bottom of the screen, but as I said, we'll go into more detail in the next lesson. Okay, so that brings us to the end of this topic. We've covered the majority of it, and next lesson we're going to be covering bonding and structure. Head over to Dr-Tutor.co.uk for my notes, which are uploaded completely for free. You can also book tuition lessons on there, offer very reasonable prices, and we can do a 15-minute free consultation if you just want to understand how the process would work. In lessons, we'll go over a really difficult exam technique. We'll use documents I've personally made from covering over 10,000 marks worth of exam past paper questions. And we'll really try and hone in on your exact weak points and make sure that you're feeling confident in the subject. I hope you found today's lesson useful. I would really appreciate it if you hit that like button and subscribe. I'm going to be producing as many lessons as I can on quite a regular basis, covering the majority of chemistry A-level and biology A-level. So if you're studying those subjects, I would hope that this is going to be useful to you. So, thank you for listening.